Good evening, ladies and gentlemen. I'm Martin Farr, co-chair of the Insights Public Lectures programme. It's usually a pleasure to welcome you to one of our events, but it's a particular pleasure today for reasons you may be aware of. This is our first in-person event for over 2 years. And this is such a joy to be seeing you in the room with us and to be meeting you outside and afterwards, rather than staring at a lens unblinkingly for an hour and then switching a machine off. It's an absolute delight, so thank you very much for coming and welcome back. The rest of the programme will also be in person, though we're recording the lecture and that will appear on our YouTube channel probably within the week. We also have an extensive archive of former lectures, and over the pandemic they were recorded, so there's video of those, audio for the ones pre-COVID. 2 items of housekeeping I've been asked to mention. There are no coronavirus restrictions in place. However, hand sanitizer and face coverings are available if you wish to use them. We're not expecting a fire alarm, so if the alarm sounds, please follow our event steward's instructions and leave via the nearest exit. As you may have seen fleetingly, we have our next 2 lectures, our next 2 events. Wednesday the 4th of May, Lord Patten, former Chancellor of this university, former Governor of Hong Kong, speaking on the Edward Heath lecture, What Has Happened to the World Order that Edward Heath helped to create? Much talk of Brexit and Ukraine and all matters in between. And on the 10th of May, the Jack Jeffrey lecture, our annual Jack Jeffrey lecture, People Powered, What If People, Not Technology, Are the Answer to the Climate Crisis, by Dr. Katie Rolick. Now, to introduce this evening's speaker, I'll be handing over to Ian Moss, Professor of Theoretical Cosmology in the School of Mathematics, Statistics and Physics. Ian.
Thank you very much. As you just heard, I'm Professor of Cosmology here at Newcastle University. It's my great pleasure to introduce our speaker today, Ed Copeland, someone I've known for a long time. This is also part of our celebrations of 150 years of science, agriculture and engineering at Newcastle University. And this is the first of our special events, the first of our colloquia, introducing the subject specifically of physics and cosmology. The Cosmology group at Newcastle was formed in 1980 by Professor Paul Davies. Very shortly afterwards, Professor Copeland joined the group as a PhD student. I joined the group at the same time. Today, we have some 20 members of Cosmology group and Astronomy group together. So this, we're pleased that this group has really prospered over the years. After leaving Newcastle, Ed went around to various prestigious institutions in the UK and abroad. Finished up at the University of Nottingham, where he heads the Cosmology group there. In 2013, his research in cosmology was recognised by the award of the prestigious Raleigh Medal from the Institute of Physics. If you want to have a look at some interesting videos on YouTube, there's a series called 60 Symbols, where Ed and other people talk about some of the most interesting aspects and news about science. So I do recommend those videos. But tonight there's no need to look at a video, you can actually see the real thing. So without any further ado, I'd like to invite Ed to step forward and give us his talk. Thank you, Ed.
Thank you very much, Ian. It's a real pleasure to be here. So I was listening to Adele at the Royal Albert Hall, and she said at one point, she turned to the audience, she said, "I've always dreamed to be here." And this is my Albert Hall moment. It's as big, don't worry, don't put yourself down. So I've sat over there and over here listening to Nobel laureates when I was a PhD student. I'm thinking to myself, God, wouldn't it be nice if one day I could come and do it? So thank you, Ian, for giving me the chance. This is going to be a bit slightly different talk. It's not all going to be about physics. Because I was here for 3 years, 3 wonderful years, I'm going to intersperse it a little bit with some of the fun things that happened whilst I was here at Newcastle. But overall, I'm hoping to give you a flavour of the kind of cosmology that I'm interested in and why I think it's an interesting topic. Probably justifies why most people that apply to university, to when they fill in their UCAS forms, will put down cosmology as kind of the big thing that they're interested in, because it's the big questions. How did the universe begin? How did structures begin in the universe? What's the ultimate goal of the ultimate end point of the universe? Is there going to be one? And we don't know the answer to any of them. So en route, though, we've found out quite a lot of things, and it's been fun doing so. And I'll hopefully give you a flavour of what the kind of things we think we understand a little bit about. So here's a picture, which I'll come back to, of this is called the cosmic microwave background radiation. So about 380,000 years after the Big Bang, the universe today is about 13.8 billion years old. So this is really early on. It's when the universe was still a baby. As the universe expanded, it cooled down. The radiation in the universe cooled down, just as if in a box, if you expanded out the box, and the radiation in that box would gradually get colder as it filled more and more of the box. It cooled down till eventually it was cold enough that the first atoms could form. The electrons could begin to bind to the protons and form hydrogen, and hydrogen atoms began to form. And this then meant that the photons, which were previously banging around against all this plasma of electrons and protons, were suddenly free to propagate, basically not interacting with anything. And what you're seeing here is an image of our observable universe taken when it was about 380,000 years old. And what I want you to look at are these hot and cold spots, the red and the blue spots. They're about 2 degrees apart in size, and these have temperatures of 2.735 Kelvin plus or minus about 10,000th of a Kelvin. These blue and red spots are plus or minus 10,000ths. Okay, so very small deviations above and below the background, which is 2.7 Kelvin. And this is crucial. And the thing that I'm going to aim at in the end is to sort of try and explain where we think these came from. Not each individual spot, but in general. And why am I going to do that? Because the evolution of the universe from this moment on led to the structures that we see today. The distributions of the large-scale structure in the universe. The distributions of the galaxies in our universe. These are, if you like, the initial conditions from which it all then emerged. And we'd like to understand where they came from. So today, the goal then is to try and provide you with a link between events occurring in the first fractions of a second after the Big Bang and the universe as we see it today, some 13, 14 billion years later. And the punchline is simple. When you look up into the universe, and of course, if you go a bit further north, you've got these absolute beautiful dark skies that you can see things really wonderfully from. And you look at the stars, and in particular the galaxies, what you're looking at is a thumbprint, if you like, left there by the Big Bang. So all you need today is a healthy imagination. Okay. But maybe before we do that, let me just reflect on life here as a PhD student. And we all have times when we're lucky, when things occur, and from it you realize a bit later on, actually, because of that event, my life took that direction, and I've got a lot to be grateful for that. And I've had a number of them. And one was back in 1982, when I was offered the chance by, as Ian said, Paul Davies, to join a group as a PhD student. And it was in 1982, and so just 2 years after Paul had first come here from King's College London. And Ian himself arrived soon after that. And what he hasn't told you was he came fresh from doing his PhD with no other than Stephen Hawking and in Cambridge. And throughout, I've learned so much from Ian. And just to be there, sort of hearing about, as I arrived as a BSc student. I'd done 3 years of physics. I'd taken one cosmology course, of which only half was cosmology. I knew nothing. I knew absolutely nothing. And so to have a chance just to learn as you're going on, it's the way to do it. And then a year or so later, another person, David Toms, arrived. And he was working on this weird and wonderful thing called Kaluza-Klein theories, which suggested that our universe may not have three spatial dimensions, X, Y, and Z, up, down, and across. Maybe it's got more than three. And I thought this was fantastic, going into these extra dimensions. So that's what I ended up doing my thesis on my PhD work on, what if the universe had more than three spatial dimensions? And I learned so much from him as well. So I had these 3 lucky breaks, and then on top of it, I came here. And Newcastle, because you live here, maybe you don't realize it until you go away, and then you realize it has so much to offer in terms of life, in terms of enjoyment, in terms of education. And it had everything someone like me could hope for. And it meant that doing a PhD definitely was, without a shadow of a doubt, one of the happiest times of my life here. And so here's the group, by the way. There's Paul Davis, who set up the group. That's an earlier Ian Moss. David Toms, a great friend of ours, Andy Wright. He had done his undergraduate degree here. He joined me at the same time, and so we were partners in crime together. He's now a senior manager for BAE. And there's Kerry Hinton, who had arrived the year before me. He was an Australian who loves surfing. So he'd ring in on a Monday morning. I'm not coming in till Thursday, the surf's up. And that was it. We wouldn't see Kerry. He would just be there. And then that was me, taken in 1982 with my mum, who I have an awful lot to thank for the support she gave me. So being here allowed me to mix physics with culture. And in those days, the Royal Shakespeare Company would come every year to Newcastle, and they'd spend a few weeks here. So we saw quite a few plays, and a couple that I remembered in particular. In 1983, we saw King Lear with Jenny Agutter, and this woman called Sarah Kesselman. And Sarah Kesselman, 5 years later, I married my wife, Natalie, and all of a sudden I was a relation of Sarah Kesselman, who I met at a party with our in-laws. And we were talking, and she said, "Oh, I'm an actress." Well, I knew nothing. And I said, "Oh, I've saw the Royal Shakespeare Company at Newcastle. I was in that." And then there she is. And then in 1985, we went and saw the Royal Shakespeare Company with Anthony Sher doing Richard III. And he died, sadly, back in December. And I was watching the news. And all the news headlines were talking about the Richard III of Anthony Sher was the pinnacle, the Richard III. And we'd seen it. I also saw Lindisfarne as well, with Andy Wright, and a relation of the Minister of Petroleum of Saudi Arabia. We went to Kevin Keegan's final game as a player. So we were there when the helicopter came down and then lifted him off. And at the time, as you do as a PhD student, we were looking after a hotel. We'd been asked by a secretary here who had a friend who owned a hotel and wanted to have a holiday, whether we'd look after the hotel. And the only conditions were we weren't allowed to take guests in. But we looked after this hotel, and I actually made a couple of bookings of various dance companies. And the hotel owners knew this Minister of Petroleum. And so we took this relation, and I like to think maybe I sowed a seed there. Just saying. Then in 1983, I did the Great North Run, having done no practice, because the guy who'd actually, got the ticket, had qualified for it, couldn't make it, and he gave me this with about 2 weeks' notice. And I seem to remember how hot it was. Then I found this picture of the 1983 Great North Run, and indeed, it's just boiling hot. And it took me, I managed to find myself by looking up Peter Cole's, and he's on the Great North Run record, and it's 2 hours, 16 minutes, and that's all consistent, because when I was about halfway around, I overheard on someone's radio them announcing the winner coming through in about 1 hour and 5 minutes. So, anyway, let's come back to a bit of cosmology. So one of the beautiful things about cosmology, it allows you to talk about lots and lots of length scales. So I'd like to just sort of remind you of some scales out there. And it also allows me to bring in some rather nice pictures. So let's maybe start with the Earth. And so this is the most famous picture, if you like, of the Earthrise from the Apollo 8 mission, taken on 24th of December 1968. Many of us were in this picture. And it's an iconic image of our beautiful blue planet. And the scale there is about 12,000 kilometers across. Okay, just to sort of set the scene for us. And we are a part of a solar system where we're protected. We orbit our sun. The sun's diameter is, rather than 12,000 kilometers, is about 1.5 million kilometers. And the typical distance between the Earth and the sun is about 150 million kilometers. And in astronomy, you introduce a new unit. They like introducing units. So 1 astronomical unit is that typical distance between the Earth and the sun. And of course, we're part of a solar system. In my solar system, I'm very sorry, Pluto's still there. I cannot quite let it go. But the typical average distance between the Earth, the sun, and Pluto is about 6 billion kilometers. So even within the solar system, we're now at 6 billion kilometers, around 40 astronomical units. And we're still nowhere in the context of our universe, even with the context of our Milky Way. And I think this is such a beautiful picture. We're very used to looking from Earth out, and we see the planets, we see Jupiter, and we see Saturn. In 2017, the Cassini satellite, which had been sent out to probe the rings of Saturn and get these dramatic pictures, turned, as it was plunging in through the ring system, turned and took a picture of the Earth and the Moon, a mere 1.4 billion kilometers away. You forget you can see both ways. And actually, the Cassini satellite, which is most famous probably for its pictures of Saturn, actually has played a huge role in cosmology. Because on its way out, it turned around to face the Earth. And they sent a message, a beam out to the satellite, which then returned it. And by doing this time of flight experiment, they were able to test general relativity to the highest precision that it has ever been tested. And so any theory that, and I will talk about 1 or 2 ideas later on, any theory which tries to go beyond general relativity is severely constrained by experiments like the one they did with the Cassini satellite. Because general relativity, which fits our universe beautifully, as I'll mention, it allows for very small deviations away from it, given the experiment like this one that the Cassini satellite did, the time of flight experiment. So we're in a solar system, we have our star protecting us, and we live within a galaxy, which is the Milky Way. Here's a beautiful picture of the Milky Way. The Milky Way is a spiral galaxy, but of course I can't take a picture of the spirals because I can't get above the Milky Way to look down at the spiral arms. So this is the Whirlpool galaxy. We live towards the edge of one of the spiral arms, and now we're talking about typical distances of the Milky Way of about 100,000 light years. A light year is the distance light goes in 1 year. Okay? It goes 100 million meters per second. So you can work out how far it goes in 1 year. The diameter is about 100 light years. A light year is about 10 trillion kilometers. And we believe a typical galaxy contains of order 200 billion stars. And we think there are of order 200 billion galaxies in our observable universe. So the question naturally arises that we can't help but ask, are we alone out there? And then we're in a universe filled with galaxies. And this iconic picture, which was known as the Hubble Deep Field picture, was until a couple of weeks ago the deepest picture ever taken. So I had to modify this from being the deepest to one of the deepest pictures ever taken of our universe. And there are objects here, I'm pointing at random because I don't actually know which one it is. There are objects around 11 billion light years away, that light has taken 11 billion years to reach us from. And you're just getting hopefully a sense of the depth and the size of our universe. The most recent one that they published had a star that they focused in on that looked like a smudge to me, and they said this is 12.5 billion years or something like that. So that's what our universe looks on these very large scales. Now let's describe it a little bit in terms of the theories and what it contains. And the theory which best describes the evolution of our universe is general relativity. And it was published in 1915 by Albert Einstein. And at the time, I mean, what he did was staggering in terms of conceptually thinking about things. In 1915, we knew about the Milky Way, but actually we didn't know about distant galaxies. There was some evidence that there were some smudges in the sky, but they didn't know what these smudges were. And in particular, they had no idea that the universe might be moving, because as far as we were concerned, as far as he was concerned, the universe was static. Of course, the stars moved relative to one another, or we moved relative to the stars, but we could explain that through our orbits. But each night, the stars were in the same fixed positions, right? Orion's belt wasn't moving apart. It was that fixed shape. And yet, his theory, what was so special about it, and which I'll come back to, is that it intimately connected the contents of the universe, the matter of the universe, you and I, and this curvature of the universe, the geometry of it, the shape. It wasn't as if we had a universe and we put matter in and the matter evolved. These two were closely linked. If the matter was present, it distorted the space-time, the curvature, to account for it. And this was a key thing that he realized was important. Within a few years, he'd written down these complicated equations. People began to solve them. And two people in particular, Alexander Friedmann and Georges Lemaitre, they showed that when they applied it to cosmology, then his equations led to a universe that was not static. It was evolving. It was either growing or shrinking. Things were moving apart or coming close together. And Einstein didn't like that, because he felt the observations showed our universe was static. Georges Lemaitre, by the way, was a priest. There he is, a Belgian priest. Another thing that general relativity predicted that Einstein also was skeptical about was the analog of electromagnetic waves. Electromagnetic waves allow us to communicate with each other, and the propagation of photons. There was an analogous system that you could have in gravity, because as matter moved around, because it was so intrinsically connected to the curvature of space-time, it caused ripples in that space-time. And those ripples would propagate out at the speed of light. And so he predicted this, but he worked out they would be almost impossible to detect on Earth because they'd be so small, these ripples. But they were detected. And in 2015, the first detection of a pair of black holes orbiting one another and coalescing, the ripples that were produced from those were detected. And if I look here, the distance that these were was 400 megaparsecs. That's about, a parsec is 3 light years, so this is over 1 billion light years away. The gravitational waves traveled for 1 billion years and passed through the detectors, detecting them, distorting them by less than the size of a proton. And they were able to pick up that signal. And there's the signal. And they did it with 2 detectors, one in Hanford and one in Livingston. And because they already had a template of what they believed the signal would look like from coalescing black holes, it matched it beautifully. It led them to announce that they'd detected gravitational waves from black hole mergers. It led to the 2017 Nobel Prize. But Ian and his fellow physicists already knew that this was going to be important work. There was a prize, there's a prize awarded here at Nottingham called the Philip Robinson Prize. And in 2010, they awarded the Philip Robinson Prize to Kip Thorne, one of the Nobel Prize winners of 2017. You'll see this is a recurring theme. Let's go back to our expanding universe. The answer was eventually determined by Edwin Hubble. Also, people would argue someone called Vesto Slifo came across this result just as a bit earlier. But in 1929, Hubble was looking at distant galaxies and looking at their velocities away from the Earth. And he showed that, as this is part of the paper, the velocity of a distant galaxy is up to a few hundred megaparsecs away, receding from the Earth is approximately proportional to their distance. So if you have a galaxy which is a meter away and a pair of galaxies which are 2 meters away, the pair at 2 meters away are going away twice as fast. So the relationship was that the velocity is some constant times the separation. And this was his original plot in his paper. He got some of the dimensions, the values wrong. The universe would have been too short-lived for this to be the actual results. But given the uncertainties in finding these galaxies with the set of instruments they had at the time, it's a remarkable result still, that he showed that this universe was expanding. It still is amazing to me, I never knew Einstein, but knowing how brilliant Einstein was, he had made sure his equations could give a static universe. He must have known those equations were what we call unstable. A small perturbation and the universe would have started expanding again. And yet he never talked about it before this period. And I just often wonder why. He must have known this. It's an undergraduate problem that we set in cosmology classes to show the instability. Somehow I just think he thought, it's got to be static. This marked the beginning of what we would call modern observational cosmology. We had, in principle, an expanding universe. It was slowing down because it had matter in there that was pulling it back because gravity sucks. And that was, when I started my PhD here, that was this scenario. It was called the cold dark matter dominated universe. But in the early 1990s, a survey of 2 million galaxies, this is called the APM survey, each of these dots here is a galaxy, suggested that all wasn't so clear. That the galaxies, when you looked at their distribution on these maps, how close is one to another, it was clustered in a way which was inconsistent with this model of a universe that only contained this cold dark matter and us. And it needed something else. And people like Jim Peebles, who won the Nobel Prize in 2019 for this work, amongst others, he was someone that said maybe there's some sort of cosmological constant, it's called, out there. And this is my second entry into this was really before anyone knew. Look, Peebles won the Nobel Prize in 2019. The Robinson Prize was awarded in 1992. So the people here, Ian and company, knew that this was going to be a very significant player. He already was in 1992, to be fair to him. So we have our universe expanding, but it's not just expanding and slowing down. In 1998, as a kind of a follow-on from the APM data, which was showing there may be this inconsistency, it was finally confirmed when people were looking at the explosions of supernovae. These are exploding stars in distant galaxies, and plotting their distance against their velocity of the galaxies. And they realized that the models, the cosmological models which fit the data the best, were those that had this type of cosmological constant. And in fact, the universe was not decelerating, it was accelerating. I pause for a moment because that means something's putting some energy into the universe to make it accelerate out. What was that source of energy that's causing this to happen? And we've dubbed it dark energy because we didn't know what it was, and we still don't know what it is. And that won the Nobel Prize for the two groups in 2011 for this discovery of the supernovae and the inference that the universe is accelerating. So that's what's happening to the universe. What about its contents? I showed you at the beginning that picture of the cosmic microwave background. They're called the anisotropies, the fluctuations in them. And I talked about 2.75 Kelvin. And so that comes from the fact that the universe is full of radiation from this epoch, which is cooling down as the universe expands. And it was measured in 2006 by the Kobe satellite with this fantastic black body spectrum. This is their data. The error bars are under this line. They're so small. And it's the most perfect black body spectrum of a temperature of 2.7 Kelvin. Now, just to remind you, Kelvin is not Celsius. Water freezes at 273 Kelvin. So 273 Kelvin is 0 Celsius. So this is at just 2.7 Kelvin. Of course, he got the Nobel Prize. This one they decided they weren't sure. They thought he has to earn this Robinson Prize, so he had to wait till 2008 to get the Robinson Prize from Newcastle. They're not going to take any old piece of data. So we have this timeline that's beginning to evolve. The universe today, this time is on the horizontal axis. Size, if you like, is the vertical axis. We're going to come back to this bit, the beginning. The universe has been expanding. There's that microwave background fluctuations about 380,000 years after the Big Bang. Photons get released and propagate to us today, and there's one of the satellites detecting it. And the universe is gradually expanding, but then recently has begun to accelerate. That's where this bit is. And in between here, about 400 million years, the first stars begin to form. A few billion years later, the first galaxies begin to form, and then gradually the structures emerge. Okay, that's the general gist. But what is everything made of? Okay, and I mentioned at the beginning, one of the fun things about doing cosmology is linking the big and the small. So what are the constituents of matter made of? So now we have to go very small, down to scales of 10 to the minus 15 meters or less. And we have what is called the standard model of particle physics. And they're made up of a set of particles called quarks and leptons, that these make up what are known as fermions. And they run in 3 families, so I've just given them different colors here. And the funny thing is, most of us, everyday matter is basically made up of these. The up and the down quarks, so a proton is made of 2 ups and a down, a neutron, 2 downs and an up. And then the electrons, so atoms are just made up of combinations of protons, neutrons, and electrons. So this family here basically accounts for much of the periodic table. Okay? And these extra quarks, they seem to be along for the ride. We need them for a consistent model of particle physics, but in terms of our everyday life, they're not playing a major role. They are in terms of detecting things and looking for particles to decay, etc. But these are what make up most of us. And then we have these wonderful neutrinos, which were thought to be massless initially, but we've realized they've got very small masses. And they hardly interact with anything. They've got no charge. So these quarks and these leptons and electrons have got electric charge, but the neutrinos don't. And then you have what we call the force carriers. Electromagnetism, the strong force that binds the nucleus together. The weak force, which accounts for things like why does the sun burn? Why do we live? Radioactive decay. Those are the vector bosons. And the gravitons, which account for gravity. So we have these pictures of our classical ideas of the forces, electromagnetism, strong, weak, gravity. And then we have the quantum side of it. We describe the force of electromagnetism via photons. We describe the strong force via massless gluons. The weak force by W and Z vector bosons. Some of you may have heard in the news recently the excitement in the world of particle physics about a claim that the W mass is more than was previously thought. Then we have the gravitons. That's proving most difficult to encompass in our theories. And then finally the Higgs, which sort of is there to deliver mass to the fundamental particles. It was the final piece in this jigsaw that they were looking for, and then they found it in 2012. But there are many unanswered questions. Why 3 generations? Why do the particles have the masses they have? We don't know the answers to these things. They're input parameters in our models. So we've got these basic building blocks. So when did the things that we are made of first begin to emerge? So the first nuclei, those are like the protons that things, began to emerge around a few minutes after the Big Bang as the universe cooled down. Hydrogen, proton, makes up about 75% by mass of the visible universe. There's so much of it around that every time you drink a glass of water, the likelihood is you're sampling some of these molecules from the early universe. So it adds a little twist to the fact I don't like the taste of this water. You know, what would you expect when it's that old? You know, that kind of thing. Helium makes up about 24% of the visible mass. So these are the lightest elements making up nearly all of the visible mass. The stuff we are made from, the protons, the neutrons, the electrons, even though they make up this amount of the visible mass, they only make up about 5% of the overall energy stored in the universe. Why? Why so little? And what about the heavier elements, the oxygen, the carbon, the nitrogen? Well, that can't form in the very early universe. That's got to form in the center of stars. But if it's in the center of stars, we can't get to it, right? So actually, we can only get to it because those stars go supernovae and they explode. And they throw the elements back out again. And then they recollapse and recombine into solar systems. So in many ways, we really are stardust. Okay? I quite like that idea. So we have this overall model explaining our universe on these scales. It's called the Big Bang. The assumptions are that on the very largest scales, the universe is both homogeneous and isotropic. Homogeneous means we're in no unique place. We are representative of any place in the universe. It is an assumption. Isotropic means it looks the same in all directions. So the photons of light, so the CMB that come in from this direction, have the same general properties of the photons of light that come in from this direction. Okay. That's the underlying assumption that we put into Einstein's equations to give us our cosmological models. Given that, and given some initial conditions which are having the universe emerge, we don't really know where they came from. Then we have a universe expanding with velocities of recession proportional to their separation. That's Hubble's law. The lightest nuclei formed within the first few minutes. That's nucleosynthesis. The universe is bathed in radiation with a temperature today of order 3 degrees Kelvin. That's the cosmic microwave background radiation. And it's old and very large, 13.8 billion years old. But there's something missing. Given the early universe was not perfectly smooth. It had these small irregularities present that I mentioned, like ripples on a pond. Given those irregularities, then gravity, Sir Isaac, can do the rest and pull them together. I have to say Sir Isaac, it's in my contract. I'm from Nottingham. Sir Isaac Newton was born in Lincoln, not in Grantham. Maybe we won't put this on YouTube. And so he has to appear. And given these irregularities, which are seen in the radiation, the development of structure can be explained through what we know as gravitational collapse. And this is a W map, the precursor of the Planck. And this is a distribution of galaxies called the CFA. I'll show you another distribution. But the problem is what caused these ripples? And I'll come back to that as I finish. So this microwave background radiation has a wonderful history. It was first detected by chance by Penzias and Wilson in 1963, for which, and you can see the green here showing you how uniform it all was. The line going across is our galaxy, and so they have to extract that bit of the curve. The lines going across all of these is light coming from our galaxy, which clearly is not from the cosmic microwave background, right? It's from stars within our galaxy. So this is the smooth initial CMB that was detected by Penzias and Wilson. They won the Nobel Prize for that. Then the Kobe satellite that I mentioned with John Mather. He won the Nobel Prize in 2006, as did George Smoot. He shared it with Mather, and Smoot's contribution was to find these first evidence of fluctuations, these hot and cold regions. You ignore the red line in the middle. That's not part of the cosmic microwave, that's our galaxy. So you're looking at these extreme regions up here. And then in 2003, the WMAP team you can see the precision's getting better and better, focusing in on more and more detail. And then in 2018, this is the Planck most recent data showing you these hot and cold spots. At the same time, you can ask, well, that's the radiation that's coming towards us. Those are the photons. What about the structures? What about the galaxies? How are they distributed? Are they showing evidence of the universe being homogeneous on large scales? So people are looking at galaxy surveys. Each of these spots here is a galaxy. There's something like over 100,000 galaxies in this survey going back in time, something like back 4 billion light years or 4 billion years. And what you can see is that there are these voids, these white regions, and then these more concentrated regions. And the evidence that the universe is homogeneous is that the size of these voids sort of doesn't keep growing. It remains the typical size that you see at smaller distances. And the reason why there's so few out here is simply that the galaxies are much further away, right? And light, the intensity of light drops off as 1 over distance squared, so you can't see them. They're much more difficult to see. It's not that they're not there, they're just very, very difficult to see out here. So the belief is that each dot being a galaxy, the universe is showing evidence of homogeneity on large scales, but I think it's fair to say that is still somewhat up for grabs. Some people still don't accept that. How can you tell how much matter there is out there? Right? You can't go into your little lab and do it, just weigh it. It's out there in the universe. You can't get to it. The only thing we've got to play with is light. This is why astronomy blows my mind. What you can infer from just light of different frequencies and different intensities coming from different directions, sometimes it gets polarized. And that's it. You couple those with your background equations and somehow you infer something about the magnitude of mass in the universe. So you have to look at the light coming towards you. And the key thing is it gets bent by massive objects because of this intrinsic coupling between the curvature of the space-time and the matter in it. Think of a trampoline surface with a big, heavy object on it and roll a marble across. That marble will then follow a trajectory governed by how that trampoline has been deformed. And that's the analog of light traveling through space-time, being through a region of space-time deformed by a large mass. It gets bent. And so this bending by clusters of galaxies, and by measuring that bend and then comparing it to your theoretical models, you have an estimate of the mass of those clusters. And we end up believing that most of the matter in the universe is dark. It makes up about 20% of the mass of matter that we require in galaxies and clusters of galaxies. Just 5% of what you and I are made of, the baryons. And it basically doesn't interact electromagnetically with anything. But the visible matter, like you and me, make up just 5%. And what and where is the dark matter? And this is a big unanswered question. We know it's out there. We know it's here somewhere. But we don't yet know what it's made of. It could be something like a WIMP, a weakly interacting massive particle. But they've not shown up. It could be something called an axion, which appears in various theories. Or recently, people have been suggesting maybe it's primordial black holes are back and showing up as dark matter, and we can't see them. But there's a big quest out there to find the nature of dark matter. Now I come to the very early bit. As I've mentioned, the geometry of our universe is related to the energy content in it, given by a parameter called omega. If this omega has a value of 1, then the universe is spatially flat. One way of understanding what that means is if I think of a sheet of paper, a spatially flat sheet of paper, if I draw a triangle, the sum of the angles in the triangle is 180 degrees. If omega is less than 1, so if there's not as much matter as I expected, the universe gets a curvature which is a negative curvature. The sum of the triangles in that case is less than 180 degrees. And if there's more matter than I would have expected, then I get a closed universe, it's called, and the sum of the angles of the triangle in that case is over 180 degrees. the evidence from the data from the Planck satellite in particular is that the universe is totally consistent with being flat today. So omega is 1. But that means that early on, when you work out the Einstein's equations, omega had to be 1 to an incredibly high precision. So basically 15 decimal places, it had to be 1. So if the universe has a curvature, it has to be, after just a second of the universe, this close to being 1 to be consistent with what we measure today. This is called fine-tuning. Why would the universe be like that? And this allowed us to, and then I've mentioned the issue of a structure in the universe. Where did that come from? This allows me to enter the final bit, which is inflation. The idea that in the very early universe, a very small patch, which was called causally connected, so it had the photons that had a chance to interact with one another and be at the same temperature, suddenly expanded dramatically in size by a factor of a billion times, in of order a millionth of a billionth of a billionth of a billionth of a second. Healthy imagination needed. Such that our observable bit, which is this red line, this red disk, at the end of inflation would naturally have been both homogeneous, isotropic, and spatially flat, because any spatial curvature would have been flattened out. And here we finish off with some of our Robinson prizes. The Alan Guth was a key person in inflation. He came up with kind of the original idea. 2001 Robinson Prize. Andre Linde, 2005 Robinson Prize. Paul Steinhardt, Andreas Albrecht, Stephen Hawking, and Ian Moss. And actually John Stewart. No? We'll stick with Hawking and Moss. Inflation explains why the universe looks flat. It just flattens everything out, stretches it dramatically. You see these examples, right? If you're at the Tynemouth beach and you look out, the Earth looks flat, even though you know, well, I hope you know, I hope you believe the Earth is curved. This field, this inflaton field, which is providing the energy for this rapid expansion, fluctuates. So some bits of the universe, as it's evolving, have a larger value of the inflaton field or its energy than other bits. Remember, the inflaton field is coupled to the curvature, because it's matter, it's coupled to the curvature. So it means that so there's my fluctuation of the inflaton field. We have this period of exponential expansion. It gets magnified. That means the coupling to the curvature gets magnified, and that's what leads to this structure here. That imprint is an imprint of these fluctuations occurring 10 to the minus 32 seconds into the universe evolving. That's why we're probing the early universe here. I think it's a nice anecdote about life here. Stephen Hawking came, I don't know if you've remembered this, you invited him in '83. And he came up to give to work with Ian. Because I checked, they published a paper together in '83. But he told us about some new ideas on the wave function of the universe, which he'd started developing in '81, but he'd written this, or was about to write this paper with Jim Hartle in '83. So we were there right at listening to him with his key ideas. Andy Wright, who I mentioned to you, who started his PhD, he did his PhD on the wave function of the universe with Ian supervising him. So Stephen gave a talk at the time. This is before he had the tracheotomy and had to have a voice synthesizer he could speak. So we were in the lecture theatre, not in here, it was lecture theatre 2, I think. And Ian was stood with him at the front, and what would happen for the first 20 minutes or so, Stephen would just be talking, sat in his wheelchair, of course. And we could hear him, but then gradually the muscles in his throat, I think, just weakened, and then it was over to Ian. And what would happen is Stephen would speak, Ian would listen to him, and then tell us what he was saying. So that's how we had the seminar with Stephen. And afterwards, Stephen said, "What do you normally do?" And we said, "Well, we normally go for a beer with our seminar speaker." And I think we all thought, well, that's not going to happen. Ian knew better. And he said, right, let's do it. It was wet. We all went walking down towards, we were going to the Cooperage, which was a pub on the quayside. And we all were walking down, I think, via the monument. And on the way down, we came to these, I think there were these steps. And we were saying, well, you just carry on down there and round, and we'll walk down. And he went, no. So 4 of us, Ian, I think you were one of them, me, Andy, Kerry, and I think it was Ian, got the 4 corners of his chair, which was very heavy because it had a big motor on it, with Stephen in it, lifted it, and brought him down there. It was petrifying. And I think it tells you about this man, right? This is what drove him. This is, not only was he brilliant, he was determined, so determined. And we got down, and then we went to the Cooperage, and he got mobbed. He got mobbed by the people there. They knew him. There'd been a TV program, I think, a Horizon program that was on around this time. But he was already pretty famous. And Stephen bought us all a drink. It was wonderful. So finally, then today, questions. What is making the universe accelerate? It's this dark energy, this weird form of energy that exists in empty space. It pervades the universe. It might be a vacuum energy or a cosmological constant or something changing slowly in time. We don't know. It's smoothly distributed. It doesn't seem to cluster. It seems very smooth. It's constant or very slowly varying. Doesn't seem to interact with ordinary matter very much. But the big problem is when you try and estimate how much there should be from the world of quantum physics, you expect there to be far more than we see. And this is a big problem that we're trying to understand. It's called the cosmological constant problem. So we finish up with an inventory of our cosmic energy pie. We have dark energy giving us about 70% today. Dark matter, 25% of the energy content today. You and I, 5%, and all the galaxies, all the stars in the galaxies. But the model seems to work. It fits the data really well. Gravity's standard model works very well. There are many issues still remain to be resolved. We need to understand gravity and quantum mechanics, how they merge together, and maybe this is where string theory might come in to play a role. We would like to understand the nature and the amount of dark energy, the nature and the amount of dark matter, the origin of the universe. How did the universe emerge in the first place? Perhaps we've got it wrong. There's no dark matter or dark energy. Maybe we need to modify general relativity, and it's all in the curvature that we've just misunderstood. It's just the baryons of you and I, and then the curvature. But every single model that has tried to do this has run up against the problem that general relativity works so well. You can't mess around with it too much. It's quite remarkable. Finally, my passport into the world of strings, I thought I might just, so in 1984, I finished my PhD in 1985, and in the late August of 84, we began to hear about this big breakthrough in the world of string theory, which was another theory of extra dimensions, and remember, that's what I was working in. And that they'd found the two physicists called Michael Green and John Schwartz from Caltech. Green was at Queen Mary College London, had found a sort of a unified description of string theory that seemed to work. And I got quite excited, and I thought I would like to learn about this. But he was in London, and I was up here, and I heard, I make it sound like we had to have smoke signals or something, but word got round somehow. The pigeons arrived and told us that he was giving a series of lectures on a Thursday afternoon. I thought, I'm going for them. And so every Thursday, every Wednesday night, I would board the Clipper bus. Does that ring a bell with you? The Clipper bus, £8.50 return. I'd get the overnight bus down to London. I was knackered. I'd go out to Queen Mary, attend a lecture, have no idea what he was talking about, but I'd have reams and reams of notes. That evening, I'd get back on the Clipper bus, get the overnight bus, come home, and just fall asleep. And I did it for I think he did about 10 lectures altogether. I went down and back and down and back. And so I ended up working on string cosmology later on, so it wasn't all wasted. So I've mentioned quite a few of these problems. These are some of the problems we would like to address. I've mentioned most of them, what is dark energy made of? What's LIGO discovering? Is it discovering these black holes? Are they from the very early universe? They're called primordial black holes. And so that's it, really. It's been a pleasure being here today. As I said, it was a dream come true for me. So thank you for listening, and thank you, Newcastle, for all that you've done.
Thank you very much, Ed. Time has really flown, much quicker than we expected, which means that the time for questions is much shorter than we expected, Ed. However, we do have 5 minutes or so, and I invite you to put up your hand if you have a question. We have a couple of microphones, and I'll be grateful if you wait till the microphone reaches you so we can all hear your question. And we've got a hand up here already.
Thank you.
I'm not a physicist, so I'll not be upset if you say what I'm going to say is nonsense. But could it be, well, my understanding is that you had the Big Bang and 2 trillion galaxies were formed within a very, very short time. Now, is it possible that with Hawking radiation, whether they were created by some nuclear event to change the energy to matter, could it be that Hawking radiation, could that be, with a nuclear event, create matter and repeat the cycle many times at different times, so you'd have a constant supply of new galaxies?
So the galaxies aren't formed immediately. But if the models are correct, it takes of over 1 billion years before the first galaxies can form. The universe is too hot early on. Any atoms that try and form, any photons of radiation have got too much energy. They smash into the atoms and just break them apart. So you end up with just a plasma early on. The universe needs to cool down enough for structures to form like atoms, and then therefore molecules, and then the constituents of galaxies. Hawking radiation is usually associated with black holes. So, and it turns out that a black hole that we might envisage evaporates incredibly slowly. And so the radiation from Hawking radiation is there, we believe, evaporating away, but extremely slowly. And so the chances are that you would not associate the Hawking evaporation of a given set of black holes with the future distribution of galaxies, which I think is what you were hoping to do. It's too slow a process for this extending over too long a period for those particles then to recombine to give galaxies, because meanwhile the universe is expanding, pulling those particles apart.
Okay. A question down here. Just wait for the microphone, please.
Hi. How large is the universe now, currently, and what is it expanding into?
Yeah. Well, we all know the centre of we know where the centre is, Newcastle, but so the universe, funnily enough, it's about 13.8 billion years, but you could actually associate a time. So you might think, okay, it's just, if that's the time and the fastest speed you can go is the speed of light, then it's that time times the speed of light, and that's giving you the distance. And I put up a number which was much bigger than that. And the reason I put up a number which was I forgot what I put something like 90 billion light years, I think. And the reason why you can put up a bigger number is that meanwhile the universe is expanding, and so things are stretching out more and more. So the universe, if you like, the observable universe is something like 90 billion light years across. That's what we think. What's it expanding into is a great question, and in these models, it's not expanding into anything. Space-time is being created as it's evolving. It's as if it doesn't have anything itself. You know, it's not that there's a box with a balloon in the box that's expanding out. It's more like the surface of the balloon, if you like. The surface of the balloon, as the balloon grows, the surface is getting larger, right? And so it's in that context that the universe is creating space-time as it's expanding. It's not a universe that's full of space-time that it's sort of filling up. That's the typical model.
Any questions? Nico, wait for the microphone.
Well, thank you very much for a nice lecture. What is your personal stance on the Hubble tension? Should we keep on exploring the tip of the red giant branch and everything, or should we also take a look at the early universe measurements?
Okay, that's good. Okay, wow. Right, so do you remember I showed an equation which was V equals h times r? The velocity of recession of galaxies is proportional to their separation. That coefficient h is called the Hubble parameter. It's got a value today. And you can estimate that value by doing sort of through different approaches. One of them you can do is the one I mentioned with the supernovae. You do these supernovae measurements, and from it, by putting in the equations for the cosmological expansion, the Hubble parameter emerges. When you do that with the supernovae measurements, you get a value for this h of roughly 73 plus or minus, I think it might be 0.5 kilometers per second per megaparsec. Really weird units, 1/time. There's another way of measuring this Hubble parameter today, and that's by using the other big thing I showed you, which was the cosmic microwave background anisotropies. It turns out that when you fit the models to the cosmological background anisotropies, one of the parameters that emerges from the model that you determine by looking at the data is the Hubble expansion rate again. Okay? Now this expansion rate from the CMB comes out to be 67.5 plus or minus 0.5. I mean, I can't remember what the errors. The errors is the crucial thing. One is 67 plus or minus 0.5. One is 73 or 74 plus or minus 0.5. They're measuring the same thing. You see a problem. You should not be getting a different answer. So what could it be? And many people have said, well, it's clearly these experiments are extremely difficult, they're full of errors. Any experimentalist knows there's systematic errors. If you don't sort out your systematic errors, you're not going to be able to say anything. These people from both camps have just put in years and years of work testing it, and they're now convinced it can't be a systematic. So the exciting thing for people like me, and maybe Ian, I don't know if you're interested in the Hubble tension, is maybe that means there's some new physics, right? That one of these two approaches hasn't included. Well, most people are fairly confident. They think they understand late-time physics. You can't mess around too much with late-time physics, the supernovae stuff. So the thought is maybe we've misunderstood what might be happening in early universe. Maybe there are some new particles out there that we just didn't realize were there and playing a role. And so people like me have been, that's what I'm currently doing, trying very hard to see whether or not, by including various new features in the early universe, we can cause the expansion rate of the early universe to appear higher, so it matches the supernovae one, yet it mustn't distort all the beautiful results of the CMB. And that's a really difficult task, and so it's not been solved. I think it's well worth putting effort into it. And personally, I think it's probably better to go to the early universe than the late. I think that's what you were asking. I think that's more likely to prove fruitful. No one wants to touch Planck. Yeah, that's right. Yeah.
I got a question here. Can you switch the microphone, please?
As a non-physicist, I find it difficult to understand how the universe is expanding no matter in which direction you look. I understand that if it's a sphere, 2 dimensions would give you rates of expansion no matter what direction you look. But as a three-dimensional man, I find it quite tricky. Why isn't it travelling at a different rate when we look into the centre, so to speak?
Well, that's a great question. I mean, as I said, at one point I said it's a big assumption we make that the universe is homogeneous and isotropic. And in terms of your question, the isotropy is actually your statement. It's the statement that in all directions that you're looking, the universe is going at the same rate. Another way of saying it is that the universe has what we call the scale factor. So we take a region of space at some time, and then at a later time, that region has remained the same shape but just got bigger. And then this is isotropy. It's remained exactly the same shape and just got bigger. And because this scale factor doesn't depend on where you are. And so this assumption is a key assumption into the cosmology, but it is an assumption. And it's one thing that people are constantly, well, not constantly, they are beginning to put more and more effort into actually testing this very question that you're asking. Is the universe expanding in exactly the same rate in all directions or not? And the data suggests it is, but the data actually it's very difficult, believe it or not, to do these because you've got to look a long way out for quite a period of time to be able to actually determine any changes. And it's a very, very difficult process. So I hear you. I think your question actually is actually a crucial one about. I would talk about it in terms of the isotropy of the universe. Is the universe anisotropic? And the data at the moment suggests it isn't. Its explanation then is we don't actually know why. You know, we don't know of a mechanism which naturally makes everything go uniformly in all directions. We can put it in as an ingredient and then solve the equations and see that they're all nicely consistent. But one of the big things that I've tried in the past to think about is I've said, well, why should the universe have done that? Why don't I just let the universe have scale factors that are different, up and down, left and right, back and forth, right? And let's just see what Einstein's equations does. And you can get solutions where it remains different, anisotropic, but they turn out to be nothing like the universe we live in. They collapse very rapidly in one direction and then expand back out again, and then they'll collapse in another direction and expand back out. These are called Casner universes, Bianchi models, they're a class of whole solutions, and they're nothing like our universe. In the context of string theory, that is something I've also thought, you know, what happens to the extra dimensions? There things have to change, right? We do not live in a 10-dimensional universe where all 9 extra dimensions are expanding out, 10 extra dimensions are expanding out at the same rate. We live, if our universe has extra dimensions, then the extra ones that look like they have to be very small and very hardly evolving at all, because we don't see them. And that would be a case of you do need to understand, if you start from a starting point where you allow them to be different, why is it that 3 space dimensions do what you're asking, whilst the others sort of collapse down to something small? And that remains, I'd argue, remains an open question in string theory to try and demonstrate that solution.
We're just going to wrap up, but we might have one special question. You still need the microphone. This will be the last question.
What is the difference of dark matter and dark energy?
Oh. You're 10, right? My word. Wait till you come and ask questions here. That's a great question. Okay, there is one. They've both got energy. So I've talked about, that's all I've talked about, energy. But there is a key difference. And that's to do with, there's another thing we often talk about when we think about particles or a fluid. We say it's got some energy or some density, but we often say it's got a pressure. And so photons of light have a pressure. It's called radiation pressure. And that's what gives a comet its tail. for example, the photon pressure pushing on the comet is a force per unit area. And matter like you and I have a pressure which is either got a positive value pushing out or zero, no pressure. Dark matter is what we call pressureless. It's effectively got no pressure. It's non-relativistic. It's not moving very quickly, and so it's not hitting anything very hard. So it's hardly producing a force per unit area. It's got no pressure. Dark energy has a negative pressure, as does the inflaton that we described that causes the universe to accelerate. In fact, our universe is accelerating today. It's inflating again today. And in some ways, that is the key difference between dark matter and dark energy. That they've both got positive energies, but the dark energy has got a negative pressure, and the dark matter has got zero, or if anything slightly, well, it's got basically zero pressure. That is how you would define the main difference between them.
Thank you very much, Ed. I do apologise that we've run over. However, it's been absolutely fascinating. So I just invite everybody to thank Ed once more in the traditional way. Thank you, Ed.